In a world where protecting information is more critical than ever, randomness plays a silent yet fundamental role. It underpins our keys, our encryption systems, and to a large extent, our digital trust. Most of the random numbers we use are not truly random. Behind them are patterns, formulas, and sequences that, given enough computing power, can be predicted and exploited. But quantum physics offers a fascinating alternative, a way to generate genuine randomness impossible to predict, even in theory. A principle that redefines the foundation of modern security and marks the beginning of a new era in data protections. An era powered by a new kind of efficiency, quantum efficiency. Imagine flipping a coin. At first glance, the outcome seems unpredictable. But if you know the position, force, and speed of the flip, you could, in theory, calculate the result. The same applies to many classical random numbers generators. They seem unpredictable, but they follow deterministic models. They are not truly random, just extremely complex. This is where quantum physics does something no other model can do. It introduces uncertainty as a law of nature. In a QRNG, we use particles of light, called photons, that pass through an optical device. The photon's path is not predetermined until it's measured. Its state exists as a superposition of possibilities. When we finally observe it, we get one of those outcomes at random, and the result cannot be predicted by anyone, under any circumstance. Quantum mechanics is the only theory that has randomness built into its core. And that's profound. We are not talking about numbers that seem random. We are talking about numbers that are random, and we can prove it. Let's go back to the photons. In a QRNG, we prepare a photon to be in a superposition between two paths. When it passes through a beam splitter, it can take either path and finally lands in one of the two detectors. If it reaches detector A, we register a 0. If it reaches detector B, we register a 1. It's like flipping a quantum coin, except no one, not even with full knowledge of the system, could predict the result. This process is precisely calibrated to ensure that the photon was genuinely in superposition. How do we know? We use interferometry, a technique that allows us to experimentally verify that the photon was in two places at once. That direct evidence is what makes the system a reliable source of genuine randomness. Most QRNGs can generate quantum randomness. But there is a problem. If something fails in the device, if a detector starts malfunctioning or the system drifts, there is no way to know immediately. The device may keep generating numbers, but they wouldn't be truly random anymore. That's where Sequre RNG comes in. Unlike other devices, Sequre RNG introduced self-testing as a standard. Every number it generates passes through a real-time verification system that ensures everything is working as it should. If something deviates, the system detects and reports it, and can either pause and alert the operators. Our device does not just generate true random numbers. It also proves through quantum mechanism that they are random. And if there is an anomaly, you will know instantly. This ability to audit randomness, even after a key has been used, is critical in sectors like defense, banking, and national lotteries, where a failure in randomness can have serious consequences. Generating true randomness is not just important, it's essential. But even more crucial is being able to prove that randomness exists in real time and based on the most fundamental laws of physics. The technology behind Sequre is not a promise. It's a reality built on over 20 years of research, and with every photon we measure, we are shaping a future that is more secure, more transparent, and more prepared to protect your digital freedom.